right? So this circle is a figure, and we have multiple chords here. All of the chords pass through this point X, right?
Okay.
So now we have seen earlier in a previous class that there is a theorem called intersecting chords theorem, right?
Yeah.
So intersecting chords theorem suggests that the product of some of the distances will be equal. So which distances? Nx into xm will be equal to cx into xd, and that will be equal to ax into xp, right?
Right.
Because three chords are passing through one single point x, we have these segments of the chords will be, product of them will be equal, right?
Yeah.
So what we will see is, we will see that time when we proved this, we proved it by similarity or congruency something, right? Now
Yeah.
what we will do is, we'll prove it in a different way. So let's try to understand what is this nx multiplied by xm. We'll prove it by the method of power of a point. So we can say that uh, correct. So let's draw a diameter through x. Okay, diameter means it will pass through O and go to the other side, right?
Yeah.
Correct. So if you draw a diameter through x, we have, let the end points of this diameter be something E and F, let's say, right? Then since this is another chord, we have nx into xm should be equal to this fx into xe, right? Correct.
Yeah.
So this is just another chord, right? A diameter is also a chord. This is a chord passing through x, right? So fx into xe should also be same, right? Now
Yeah.
what we can say is, this fx can be written as of minus ox, right?
Yes.
And the fe xe can be written as ox
Plus
plus
OE.
oe, right? And OF and OE are basically radius. So we can write R minus OX, and we can write R plus OX, right?
That's R squared minus OX squared.
Hmm. So we get that this whole product is equal to R square minus OX square, right?
Yes.
And this quantity, radius square minus distance of the point from the center square, this quantity is sometimes called power of a point. So what we will say is, we will define power of a point x as follows: power of x with respect to a circle will be ox square minus r square, where o is the center of the circle, o is center of the circle, and r is radius. So r is radius, O is center. So OX square minus R square is power of a point X. So this is basically negative of the power. So generally what will happen is, if the point X is inside the circle, the power will be negative because radius will be bigger than this, right?
Yes.
So if the point is here, your OX, this distance is smaller than the radius, therefore it comes out negative. If the power of a point x is greater than 0, then x is outside, right? Outside the circle. And if the power of a point x is equal to 0, it is on the circle, correct?
Yeah.
So this definition will turn out to be useful because we will use that to prove certain other results, okay? So for example, we can now say that this property, if a point x is outside the circle w, which is denoted by o and r, o is the center of this w circle and r is the radius. then the power of point x equals the square of the length of the tangent segment from x to the tangent point t, from x to the tangent point t. Okay, so what this means is basically draw a circle. Let's say x is outside the circle, you have O here, and radius is r. Then power of point x, how will we write that? That will be ox square minus r square, right?
Yeah.
So ox square minus r square, and that he's saying is equal to length of tangent segment from x to tangent point. So uh, if I draw a tangent from x to another point t here, right? So this is my t point, right? This is tangent, correct?
Yeah.
So I am saying that length of xt square, right, is equal to power of point x. Why? Because that is clear, because this is also radius, right? And this is 90
Yeah.
degrees, right? And then ox will be hypotenuse, correct?
Yeah.
So you have ox square should be equal to xt square plus radius square, and therefore xt square is equal to ox square minus radius square, which is power of x, right?
Yeah.
So basically power of x comes out to be equal to the square of the length of tangent from a point outside the circle to that circle, right?
Yes.
So this will help us in situations where we have to estimate the length of the tangent. If you have to estimate this length, then now you can say it's power of point x with respect to this circle, right?
Yeah.
So we will see examples of that soon. Now the next thing that we will do is the famous Euler's theorem, uh, which we briefly looked at in properties of triangles also. Like there was a question where we said we let O and I be circumcenter and incenter of a triangle. We want to
Yeah. It
find
was
out.
like something like find the distance between it or something like
Mm,
that, I think.
so we have to find OI. Okay. And when we were doing properties of triangle, we got it by actually drawing stuff and all. Like we drew our ABC, and in SL only there is a derivation using cosine rule, right? But that
Yeah.
derivation is slightly long. There is another proof, there is an alternative proof for that also, which is by power of a point, which is by circle properties. So what we will do now is try to get the alternative proof. This is my in center angle bisectors. Let's draw ortho circumcenter. Circumcenter will be like this and like this. So let's say O is here. We want to get the distance OI, right? And
Yeah.
what I will do is I have to prove that OI square is equal to R square minus 2RR. This was the result finally. Okay,
Oh.
we have to prove this. Uh, okay, so I have my incenter and circumcenter. Let me draw the in circle and circumcircle both. So let's say something like this is my in circle. This is my in circle, and this is the point where in circle touches this side, F. So Fi will be perpendicular, and Let's also draw the circumcircle. Circumcircle will be like this, and passing through C like this, circumcircle, right? And we can say that, let's say A to I, this line, right? This line cuts the circumcircle at D. Okay, correct? I'm just
Yeah.
extending the AI line to D. Okay,
Yeah.
so now what else can we say here? O to D also, can we join? Uh, okay, what I can say is, from, one second, just hold on. I'm getting a call. One second. Okay, so we have this D point, right? Now
Yeah.
from D point, obviously D lies on the circumcircle, so we can connect it to the center of the circle and extend it like this, right?
Yeah.
This can be my diameter of the big circle, right?
Yeah.
So I have just done that. Uh, now now what we need to prove is that OI square is equal to R square minus 2RR. So that means that OI square is equal to R into R minus 2R, right? Correct.
Yeah.
So OI is this one. Correct.
But are Fi and O colon?
What?
How is O? We need to. Oh, you're saying we need to prove that. Yeah.
We need to prove this distance. So, okay. So AI into ID, right? AI into ID is like a point. What is AI into ID? It's like intersecting chords theorem, no? Right?
Yeah.
AI into ID. It's on the big circle. So that should be equal to power of I with respect to big circle, right?
Yeah.
Circumcircle, right?
Yeah.
So power of I with respect to circumcircle will be what? OI square minus capital R square, right?
Yeah.
Correct.
Yeah.
So what we need to show is that now we have OI square is equal to, actually, if I notice that this distance will be positive, length into length, I have to write this as R square minus OI square, no? Because this is
Yeah.
I is inside the circumcircle, right?
Yeah.
So all I need to show is that OI square, since it is equal to R square minus AI into ID, right?
Yeah.
I need to prove what? AI into ID is 2R into R, right? This is what I have to prove, no?
Yeah.
Then I would get OI square is equal to this, right?
Yeah.
Correct. So,
Yeah.
okay. Now, we have earlier proved that the length DI and DB will be equal. the length DI and DB will be equal. If you remember when we started proving in center and all, no?
Yeah.
If I join this, for example, this one, right? Like,
Yeah.
so, can we prove that DI is equal to DB again? Just think about it. Using some angles and all, I think we should be able to do it. We know this angle actually. This angle will be equal to this angle, let's say x plus b by 2, right?
Yeah.
Correct.
Yeah.
And this angle x is the same as this angle.
Yeah.
This is the same because of this arc, right?
Yes.
So basically what
Yeah.
we have is this is b by 2 because this is no, this is a by 2 because this is a by 2 and this is b by 2. So this total angle is a by 2 plus b by 2, right? Right.
Yes.
We have this angle is coming as a by 2 plus b by 2. And what about this angle? Can we also get that? We have to prove that this triangle is isosceles basically, right? To prove di is equal to db. So I am trying to get now this angle. This angle will be uh,
Wait. I know what it is. Wait. It's
exterior angle of
look.
this.
Yeah. A by 2 plus B. It's 180 minus A by 2 plus, which is equal to
You don't need
90
to do
plus.
anything. You need to just say this is exterior angle of this, no, this triangle.
Oh yeah.
This is a by 2
That's
and this is
90.
b by 2,
It's 90 minus A by 2 plus. Oh,
right?
yeah.
So you're getting isosceles triangle. So you'll have di is equal to db. So di is equal to db we already have. Now we need some similar triangles. I need to prove AIAD is 2RR, right?
Yeah.
I will just rub off some unnecessary stuff. 1 second. Now I know di is equal to dp, so I'll just mark this and this. To prove this, this looks like a similarity question, no? Like it's uh, like if you find the right triangles, you can prove it by similarity, no? This
Yeah.
type of thing. So what we have to look for is a triangle that has the sides AI, some triangles which have sides AI, DB, BD. Somehow we need to get smaller and 2R also, right?
Yeah.
Correct. So obviously this FI is smaller, by the way, right? FI
Yeah.
was smaller, right? And that's fine. Then and DE is 2R, right? 2 capital R, right?
Yeah.
That is the diameter, right? And
Yeah.
therefore, since it is diameter, you have angle EBD will be 90 degrees, right? Because angle in a semicircle, if I make join this, right?
Yeah.
Like this, right? Correct.
Correct.
So now we have IFA, this angle is also 90. And so obviously there is a right angle triangle AIF and there is a right angle triangle EBD, right? Notice this right angle triangle and the biggest right angle triangle here, right? Correct.
Yes.
So let's look at least they have some of the sides that we want, because AIF has IF, which is small r, and this has 2 capital R, right? Correct.
Correct.
So we can look at these two triangles, triangles AIF and triangle EBD, and look for similarity. So now what angles are same? Okay, obviously this angle is same as this angle, right? Because same arc, right?
Yeah.
Arc BD is subtending this angle and same angle here, right? And one angle is already 90-90, right? Two angles are equal, right? Correct.
Yes.
So the triangles are similar. This is similar to this because of AA, right?
Yes.
So then you can say AI by IF, AI by IF will be equal to ED by DB, ED by DB. Why? AI is the angle of is the AI is the side opposite to 90-degree, and similarly ED is the side opposite to 90-degree, and IF is the side opposite to angle A, and BD is the side opposite to angle A, right?
Yeah.
Right. So what we
Yep.
get is AI into uh, AI into DB, right, is equal to ED into IF, right? And ED into IF is actually 2RR, right?
Yeah.
And we have just AI into DB, we have DB, and DB is equal to DI, right?
Yes.
So we have AI into DI is equal to 2RR,
Correct.
and then we have OI square is equal to this, no?
Yep.
So basically, what are the things involved in this proof? The things involved are, first of all, realizing that this OI square is equal to this looks like power of a point I, right? Somehow. So if I write power of a point I with respect to the big circle, circumcircle, right?
Yeah.
It will be, you'll have to write it as R square minus OI square is equal to
Yeah.
your AI into ID, right?
Yep.
Because if it is power of a point, it will also follow that intersecting segments theorem, intersecting chords theorem, right? That product
Yes.
should be equal to power of a point, right?
Yeah.
So if I wanted to find OI square, I need to just estimate this part, because R square is already coming, right?
Yeah.
AI into ID is what I need, AI into ID. And now I realize that DI is equal to DB, right? So AI into ID is actually AI into BD, right?
Yeah.
Why is DI is equal to DB? Because simple isosceles triangle, you can prove that this is isosceles, this one, by angles, right? Because this is B
Yeah.
by 2 and this angle is equal to A by 2. And similarly, this angle is equal to this plus this, which is A by 2 plus B by 2, right?
Yep.
So if I wanted AI into DI, it is actually just AI into BD. And now what I need to do is prove that that is equal to 2R into small r. And 2R is one length diameter here. This is one 2R length. And Fi is a smaller length, right? So I have to look at this triangle and the biggest triangle here, EDB. And those two triangles are similar by AA.
Yeah.
And since they are similar, and I will just write the ratio and it will come 2RR, right?
Yeah.
So that is
Yeah.
the proof for this. Now, from here, we can also get an inequality, because we can say that OI square is non-negative and R is always positive, right?
Yeah.
This has to be non-negative, greater than equal to 0, and R is always positive. Therefore, you get r common. This must be always positive, right?
Yes.
So in any triangle, you will have r is greater than 2 small r. When is equality happening? When this distance becomes 0, right? Equilateral triangle. Only for equilateral triangle. Why? Because whenever it becomes equal, r is equal to 2r, OI will be 0, right? Correct.
Yeah.
If OI is 0, it means circumcenter and incenter are the same point, right?
Uh, yeah.
So that happens only in equilateral triangles. Are you
Two.
understanding?
Yeah. You're saying basically um the radius of the circumcircle is twice the radius of the incircle in a equilateral
Equilateral. And
triangle.
otherwise it will be bigger,
Bigger. Okay. Okay.
right?
Yep.
So now, have you written down all of this stuff, this part?
Yeah. Just give me a minute. I'm trying to finish that
Hmm.
one. Okay. I'm done. We can move on now.
Hmm. So the next question where we'll utilize this is actually a International Maths Olympiad 2009 question 2. So IMO 2009. So this question says that let ABC be a triangle with with circumcenter O. The points P and Q are interior points of the sides CA and AB respectively. Respectively. Now let K L M be the midpoints of BP, CQ, and PQ respectively, and let tau be a circle through K, L, and M. Now suppose that line PQ is tangent to the circle tau, is tangent to the circle tau. We have to prove that OP is equal to OQ, the length. Okay. So looks like a very long sort of a question. Just go step by step and try to draw the figure.
Yep.
Right. So we'll just try that. ABC, let's say A, B, C, and we have a circle. Let's say center here is O, and circle for ABC is like this. P and Q are interior points of CA and AB. So let's say P is somewhere here, Q is somewhere here. This is P, this is Q. K, L, M are midpoints of BP, CQ, and PQ. So BP is this line. BP, CQ is this line. And PQ is this line. So K, L, M are midpoints of that. So K is somewhere here. L is somewhere here. And M is somewhere here, right?
Yeah.
Okay. Now we know that line PQ is tangent to, okay, there is a circle passing through KLM, right? This is called tau circle. KLM have a circle passing through, and line PQ is tangent to the circle, right? So PQ is
Yes.
like a tangent. So if I draw a circle like this, it touches here, and circle is like this, something like this, right? Passes through K, passes through L, passes through M, but is tangent here, right?
Yeah.
This is my situation. So, okay. Now we have to prove that OP is this distance is equal to OQ is this distance, right? Correct.
Yes.
Okay. So you can draw a slightly bigger figure. My figure is a little small, but draw a slightly bigger figure so that it's a little more clear. It's not difficult to draw the thing. Like there's no difficulty in the figure. It's just too many points are there, so you need to draw it big. Now make sure once you have drawn it, tell me.
Yep.
So we have to prove that P and Q are equidistant to O, and O is what? O is circumcenter of the big triangle, right? Correct.
Yeah.
So if 2 points are equidistant from a circle center, right? Suppose 2 points are here, and this
Yeah.
distance is equal to this distance, then we can say that the power of the point X is equal to power of a point Y with respect to the circle, right?
Yeah. Yeah.
Right? Then only they will be equidistant, no? Because power of X would be what? OX square minus R square, and power of Y would be OY square minus R square, right? So if power
Yes.
is equal, then OX square is equal to OY square, right? Correct.
Yeah.
So what we need to show, we need to prove that power of P is equal to power of Q with respect to circumcircle, right?
Yes.
Okay. Power of P and power of Q with respect to circumcircle. Now think about it. This power of a point, if it was a chord, like P is lying on a chord on the circle, no? On the circumcircle, right?
Yeah.
P is part of the AC chord, right? And Q is part of the AB chord, right? Correct.
Correct.
So we saw earlier that whenever it is part of a chord, you can say that AP into PC is equal to power of the point, right?
What? Yeah.
AP into PC is equal to power of P, right?
Yes.
And similarly, we saw that AQ into QB should be power of C, right?
Yeah.
Correct, no?
Yeah.
Because
Correct.
I could have joined the diameter and made it like this, right? AQ into QB will be equal to XO, XQ into Q, whatever diametric point, right? Y,
Yeah.
right? And that would be your power of a point, Q, right?
Yeah.
So ultimately, in order to prove that OP is equal to OQ, you have to prove just AP into PC is equal to AQ into QB, right?
Yeah.
Because that will mean power of point is equal, and that will mean they are equidistant, right?
Correct.
So great. So now the question is, instead of trying to prove this, we'll try to prove that AP into PC is equal to AQ into QB, right?
Yeah.
Correct. Now, uh, okay. So now notice, if you have drawn a figure, you will notice that M is the midpoint of PQ and K is the midpoint of PB, right? That was given.
Yeah. So that means that by MK
MK.
is half of QB.
Hmm. MK is half of QB, right? By
Yeah.
midpoint theorem.
Yes.
Okay. And similarly, L is the midpoint of QC, right? L was midpoint of QC, right?
Yep.
And P was midpoint of M was midpoint of PQ, right? So if you look at triangle PCQ, right? In triangle
Yeah.
PCQ, L and M are midpoints, no?
Yes.
Because M is midpoint of PQ, L is midpoint of CQ, right? So you can say again, LM is equal to half of PC, right?
Yeah.
Correct. So we have this result by midpoint theorem and this result by midpoint theorem, right? I'm going to rub off this page. I'm going to do it on the next screen, okay? Because I need the space. I'll just write everything there. I'll just not write the question. So the thing is, we need to prove AP into PC is equal to AQ into QB, right?
Yeah.
And we have already stuff that MK is parallel to QB and MK is equal to half of QB, and we also have ML is parallel to PC, and we have
Yeah.
ML is equal to half of PC. right? Correct.
Yeah. Yeah.
Now the circle was tangent to PQ line at the point M, right?
Yeah.
Correct. So
Yeah.
circle, look at your figure, I'm not drawing it again. Circle tau is tangent to PQ at M, right?
Yeah.
Okay. So now angle, like we have alternate segment theorem, right? Alternate segment. Like angle that the tangent makes with a chord, right? So if we have a
Yeah.
PQ line here, let's say, right? And we had a circle like this,
Mm.
right?
Yep.
This was our point M, and somewhere here was our point L, and somewhere here was our point K, right?
Yeah.
So if I join like this, KM, because KM was parallel to our BC type thing, right?
Yes.
KM was parallel to BQ, right? So, and if I join this, I know that angle KLM, this angle, should be equal to this angle, no? K
Yep.
and Q, right? By
Yeah.
alternate segment theorem, right?
Yeah.
Correct. And K
Yeah.
and Q is equal to uh, KMQ is equal to MQA, right? Because parallel line, this was parallel to this base.
Oh, yeah. Okay.
You remember right now we had said that KM is parallel to QB, right? And QB is part of AB, right?
Right.
So KM is parallel to AB, right? So we have this angle equal to this angle and this angle equal to this angle, right?
Oh, yeah.
Correct.
Yep.
So what we get is angle KLM is equal to angle PQA, right?
Yeah.
And we get LKM, this angle, LKM, right,
Yeah.
is equal to LMP, this one, obviously same theorem, right? Angle LKM is equal to angle LMP, right?
Yeah.
Again, alternate segment theorem only, nothing else. And from there, we can say LMP should be equal to MPA, right? Because we also got LM was parallel to this line, right?
Yeah. Yeah.
Because we had written here LM parallel to PC, no? And PC is part of AC, right?
Yeah.
So this is equal to this, right? LMP is equal to angle MPA, right? And
Yeah.
MPA is equal to angle QPA, you can write it QPA. MPA is same as QPA, right?
Yeah.
Correct. So what
Yes.
we are getting is triangle APQ. APQ is clearly similar to triangle KLM, right?
Yeah.
Because in triangle APQ we have two angles. This angle is equal to this angle and this angle is equal to this angle, right?
Yeah.
Correct.
Yep.
So we get now similarity condition here. We get AP by AQ, right? AP by AQ, the angle, the sides opposite to this and this, right, should be equal
Yeah.
to MK by ML, right?
Yeah. Yeah.
Correct. And
Hmm.
MK by ML is actually half of QB and half QB by half PC, right?
Yeah.
So it is QB by PC. So you get AP into PC is equal to AQ into QB. You understand? We have gotten similarity of this triangle here and this triangle here, right?
Yes.
If you have gotten similarity, you can write AP by AQ is equal to MK by ML, right?
Yes.
And those are by midpoint theorem, those are equal to, that ratio is equal to QB by PC, right?
Yeah.
So now we got AP into PC is equal to AQ into QP, right?
Yes.
Which means that power of point P is equal to power of point Q, which means that OP is equal to OQ. Okay.
Okay.
So the idea here was this alternate segment theorem is important, because without that you would not have gotten this angle equality, right? This
Yeah.
equality was important here. This was X, and no, this was not X. This was not X. This was X.
But that's why alternate segment theorem only, right?
And this was Y, and this was Y, right?
Right.
This is by alternate segment theorem. This is angle between a tangent and a chord, and that same chord subtends the angle X here.
Yeah.
Similarly, the same tangent and a different chord, and that different chord subtends the angle Y here, right?
Yeah.
So that alternate segment theorem was important, because if you got that, then you can say that parallel lines, therefore this angle is equal to this angle, because this became X. No, this angle is equal to this angle, and this angle is equal to this angle. Parallel lines we already had by midpoint theorem.
Okay. Yeah.
So, so we are using power of a point, we are using midpoint theorem, and we are using alternate segment theorem and similarity, right? The four
Yeah.
things: power of a point, alternate segment, midpoint theorem, similarity. And then this is your international maths Olympiad question.
Yeah.
So nothing very fancy, in the sense like nothing so much theory that you don't know the theory. Like, it's just about being able to
Creativity.
not get scared of the question, like trying it, and stuff that you already know has been used, right?
Yeah.
Okay. So that is an example of power of a point, how we use power of a point in situations. Uh, we'll stop here, because there is one more thing that I want to tell you, but I feel like
Um.
that'll be too much for now.
Can
So,
I can I can I
uh,
finish writing it down first?
yeah, yeah.
I think I'm done.
Okay, so next class onwards, we'll probably switch to other topics. So algebra and all. There is a few things more in geometry, but we'll come back to it later when the time comes. So get your list of stuff that you want to discuss, or send it to me by tomorrow. Maybe I'll look at it once. Okay.
Okay.
Topics that you need to get help on. So we'll, if you send it to me by tomorrow and all, we can plan out what to do Friday onwards. So probably we'll start Friday with logarithms, and after that we'll see what else is there. Okay.
Yeah.
Okay. That's it for now. Bye.
I'm sure.